Now, in section 3.4, we're going to look at something called the standard normal distribution. Now, we've already mentioned that there are loads of different types of data that can fit a normal distribution. So you might have the height of adult males in a certain population, or one of the examples we talked about in an earlier video was the weights of tigers in a jungle, for instance. And we've seen examples in the textbook already where you have something like the diameter of plates in a certain manufacturing process, and the diameters of these plates are subject to a normal distribution. Now, the thing is, there are infinitely many normal distributions because there are infinitely many data sets, given that you can have any mean and you can have any standard deviation. So you could have a data set which looked, let's imagine 0 is here. You could have one with a really high mean and a really small standard deviation like that. Or you could have a different data set with a lower mean but a larger standard deviation, so the data looks more spread out, and there's all sorts of options, aren't there? Now, back in the days before these fabulous calculators, you couldn't analyse any of these distributions with different means and different standard deviations unless you first transformed them to fit one single standard normal distribution. And once you'd done that, you were then able to look at large tables of values for this normal distribution and work out probabilities for this one, and then kind of undo your change to work out the corresponding values for the data you were working with. Of course, we've got these calculators now, but there are still times where we need to do this process, this standardising of the normal distribution, especially when we're dealing with unknowns and we're dealing with algebraic equations rather than specific numbers. So you need to learn the process of standardising the normal distribution first, and then you'll have a look at some more complex examples in the next video. So the process of standardising the normal distribution looks like this. You take the normal distribution that you're dealing with, we call it X, don't we, capital X, and first of all you shift it left or right so that its mean is now located at 0. So first of all, we're going to take, let's say if X is normally distributed with a mean of mu and a variance of sigma squared, then we do this. To turn it to a standard normal distribution, for which we use the letter Z exclusively for this one, then let's put to standardise, we do the following. To get Z, we take our X values and we subtract the mean from them. So if the mean was like over here, let's say the mean for that one is 20, if you subtract 20 from all your values, your mean would now be 0. And every single one of these values here has 20 subtracted from them, so that the mean of the new data set is at 0. So it's like taking your graph and just shifting it to the left. Then, once you've done that, you need to make it so that the standard deviation out to the points of inflection is only a distance of, you can tell how rubbish my drawing is only a distance of 1 away from the mean, so that that's at -1 and this is at +1. So what we have to do there is either squash or stretch the curve so that it fits into this shape instead of these shapes, for instance. So to do that, we divide by the standard deviation. So a standard normal distribution looks like this, same as the others, but we call the horizontal axis Z in this case. And it has a mean of 0 and a standard deviation of 1, meaning a variance of 1 squared, which of course is also 1. And this coding here that we do to all the data is really important. You need to make sure you learn that because you're going to have to apply it in all sorts of different scenarios. So what we do essentially is we standardise, which means we turn X into Z by subtracting the mean and dividing by the standard deviation. So let's just have a look at a quick numerical example first. We have a data set whose mean is 50 and whose standard deviation is 4 or variance is 16. And we know that this is normally distributed data. Now, the one thing before we answer this question I've just realised I didn't mention is the area under this Z curve, this standard normal distribution curve, the area to the left of any point is called phi, and that's a capital Greek letter phi of Z. So let's say, for instance, this area here to the left of 0 we would call capital phi of 0. Or this area here to the left of 1 we would call it capital phi of 1. So in more general terms we can say this: the probability that z is less than a smaller value z, lowercase z, is written as phi of that lowercase value. And that lowercase value there being, of course, the value on the horizontal axis, but the answer to this being the area under the curve, or the probability. So if we want to find the probability that x is less than 53, we know we can use this inverse, we can use the cumulative normal distribution function on the calculator, but what I'm interested in first of all is just can we apply this transformation to write it as in terms of z instead. So the probability that x is less than 53 is the same thing as the probability that on this curve z is less than 53 minus the mean of 50 and divide by the standard deviation of 4. There. So that is the probability that z, notice how we've changed our letter now, is less than, that's 3 over 4, so 0.75. So that means we can write it as phi of 0.75. So then let's have a look at the next one. We're now dealing with the probability that x is greater than or equal to 55. Remember in a previous video I told you don't need to worry about the equal to bit because the probability that it actually equals 55 itself is 0. So whether you write that with or without the equal to bit doesn't make a difference. So I didn't draw a diagram for this one. I should have done. Let's come back and just show you what's going on here. We are dealing with, this is the standard normal distribution now, so the mean is at 0. We're finding that area there, and that area is the same as the area being less than 53 on the original curve, and with this value being 0.75. So this time let's draw it properly from the start. So if I were to draw this on a normal distribution, I would draw my curve, I would mark on 50 in the middle, I would mark 55 a bit higher, and I would shade the area to the right. So it would look something like this. And that would be the probability that I would be trying to find. Now, for the purposes of this, though, we are going to standardise it to z. So that area there is the same thing as taking the standard normal distribution, going through 0, and finding the area, dropping my pens, finding the area bigger than this value here. And that's the value that I want to find. So we can say that the probability that x is greater than or equal to 55 is equal to the probability that z is greater than or equal to, and then we now apply the transformation. So we go 55 minus the mean, divide by the standard deviation. So that's the probability that z is greater than or equal to, what have we got here, 5 over 4 or 1.25. But phi is always the area less than a value. So phi of 1.25, let's mark on 1.25 here. So that was 1.25. But phi of 1.25 is this green area here. And I'm not interested in the green one. I'm interested in the blue one. So to find the blue one, I would have to subtract the green one from the number 1. So this that I'm interested in is 1 minus phi of 1.25. The question doesn't want me to actually work out the answer, it just wants me to leave these in terms of phi of z. So that's done there. Now let's have a look at example 7. So in example 7, we're told that the systolic blood pressure of an adult population is given by the letter S, and it's modelled as a normal distribution with mean of 127 and a standard deviation of 16, so we write a variance of 256 or 16 squared there. Now, a medical researcher wants to study adults who have a blood pressure higher than the 95th percentile. And we've got to find what the minimum blood pressure is for an adult to be included in this researcher's study. So what we know is that someone is included if the probability that their blood pressure is greater than a particular value, let's call it lowercase s, is 0.05. Because the 95th percentile means the chance that you are less than it is 95%. So chance that you're greater than it is 5%. So only 5% of people are above the 95th percentile. So now, let's have a look at how we're going to work this out then. What we know is that we can standardise this. So we'll say that this bit here, this statement, can be turned into the probability that z is greater than, and now we apply this transformation or this coding to the lowercase s. So s minus the mean divided by the standard deviation. And we know that that is 0.05. So I'm just going to draw a sketch at this point so I can picture what's going on. On my standard normal distribution, going through 0, we have the chance of being greater than the value that we've called s minus 127 over 16. That chance is 0.05. Now what that means is the chance of being less than it, of course, is 0.95 because we're dealing with the 95th percentile. So I'm going to use my inverse normal function to work out what this value is here for the standard normal distribution. So we'll go to option 7 and inverse normal, and my area is 0.95. We have already, it defaults to z because you'll see that sigma is 1 and mu is 0. So that gives me 1.6449. So I know that this value here is 1.6449. So let's write a note of the calculation we're dealing with. We have, therefore, that s minus 127 over 16 is in fact the number 1.6449. And then let's undo this. So 1.6449 times by 16 and then add 127 gives me 153.3. What are the units? mmHg. So somebody will be included in this study if their blood pressure is greater than 153.3. Now you can have a go at the next exercise, which is exercise 3D, please.